Hello everyone. I am Anuj Kumar. I am working as a Prime Minister Research Fellow at IIT Roorkee, and I am also a TA in this course that is trace and ultra trace analysis of metals using atomic absorption spectrometry. So, uh, Here is the first question for this assignment 5. That is, you are asked regarding the flame atomic absorption spectrometry. So, in flame AS, metal oxides are reduced to metals by the free energy available from. Okay, so basically, you have to define the free energy, the source of free energy, which reduces the metal oxides to metal in the flame AS, you will get from. There are four options: carbon monoxide and hydrogen gas, both carbon and hydrogen radicals, carbon dioxide and hydrogen gases, either carbon or hydrogen. So I'll wait for 2 minutes and after that I'll discuss this particular question in detail. Right? Okay. Check. Okay. Okay. This is basically the explanation for this question. The temperature of the flame plays an important role in the volatilization of salt, after which the thermal dissociation process of molecules into atom begins. This is a basic phenomena taking place in the flame AS. Okay, so this is a phase where mostly non-spectral interferences occurs. So in the flame, a variety of combustion products, such as these products, are present, right? So I want to say that the chemical environment and the temperature and residence time of the chemical species in the flame have a greater influence on the concentration of atoms in the flame. Right? If the concentration of atoms is low, you will get a lower signal in the AAS. Right? So temperature is playing a greater role here. Okay? Let me So, carbon monoxide and hydrogen do not have a sufficient free energy to reduce metal oxides. But during the oxidation of carbon or hydrogen radicals, enough free energy available to reduce more stable oxides, right? So, the statement is clearly written here. You can choose the right option from seeing only this statement. So, there are many statements here you can read for your or knowledge, that is C2 and CH radicals are found only in the lower zones of the flame. Okay, and the hydrogen radicals remain longer in the flame. That is, the residence time of hydrogen radicals is in the flame is very high. Okay, and hence they play an important part in the production of atoms via thermal dissociation. Okay, and carbon monoxide and hydrogen, they do not have sufficient free energy, I have already discussed. Okay, so from this you can choose the right option, that is the second one. Both carbon and hydrogen radicals provide the free energy to inflame AAS, that basically reduces the metal oxides to metals. Okay, so you can read this much of statements for this uh, question. Okay, so now I am going forward to the question number two. That is, you are asked about the effect of organic solvents such as acetone, methanol. MIBK is basically methyl isobutyl ketone, isobutanol, etc., are advantageously used in AAS because they increase the sensitivity of determinants. So this effect can be attributed to the first is the lower viscosity of organic solvents, formation of complex with metal ions, increase the temperature by exothermic reactions, and formation of free radicals in the flame. So what phenomena is important for increasing the sensitivity of determination for any metal? Basically, you have to explain the role of organic solvents. Okay, so I'll wait for 1 minute, and after that I will explain. Okay, so the effect of organic solvent basically lies in the transport influences. Okay, you have read about the various interferences that taking place in the AAS. Okay, so the transport influence is basically describing the mass transfer, right? Okay, so this depends on the rate of aspiration, physical characteristics such as viscosity, surface tension. Okay, and basically the transport influences are observed when you observe the increase in the salt concentration. Okay, because whenever you increase the salt concentration, you will observe the greater droplets of salt. Okay, second is the organic macromolecules such as proteins and sugars, and last is the organic solvents. So basically this question is specifically about the organic solvents. Okay, so uh, uh, let me explain some details about this effect of organic solvent. Okay, for example, if you dissolve any sample in methanol, okay, so the density of methanol is very less compared to water. Okay, so if the viscosity, or you can say the density of methanol is very less, so the sample uptake will be very high because the less force is required to pull the sample. Similarly, vapor pressure. If the sample solvent is having a very low boiling point, the aspiration and other things will be affected because salt concentration, density, pressure, and all these things will increase. Okay, so if mostly this kind of situation, that is I was discussing about the bigger droplets you can observe in the seawater because the seawater contains high amount of salts. Okay, so whenever the sample containing organic solvents are introduced into the flame, exothermic reaction take place and production of with the production of carbon monoxide and the carbon dioxide, right? But exothermic reaction also means higher temperature of the flame. Okay, so higher the temperature of the flame, more would be the free atom concentration. Okay, so in our AAS we basically need the free atom concentration, higher free atom concentration for the higher absorbance, right? So in this particular table you can see the effect of particular organic solvents in the determination of copper matter, right? If you see here, if I increase the acetone content from 40 percent to 80%, right? So the relative sensitivity increased from 2 to 3.5. Okay, and this relative sensitivity is measured with respect to water. Okay, as I had described here. So the effect of organic solvent plays an dominant role in the determination of metals. Okay, so in the four option, the most appropriate option will be this one: the increase in temperature of the flame by exothermic reactions. So now I am going forward to the third question, that is in AAS, dissociation process frequently takes place between the flame gases, and these ions cause. Okay, so if there is a flame and dissociation is happening here, right? This dissociation happening here, so the ions which are produced by as a result of this dissociation, what they create in the, what type of interference they create in the signal. Okay, so they can create so they can enhance the analytical signal or decrease, or they can cause no change, and last one is the none of this. So here you can see the dissociation process frequently take place between the chemical species and flame gases. Okay, so the variation in the concentration of halide, free radicals, the cyanogens and hydroxyl radicals, this type of radicals in the flame gas can influence the dissociation equilibrium. Okay, so these are the dissociation reaction. Basically, you can observe in the flame. So what is the function of these? What is the influence of this dissociation? What they do? Okay, so these ions suppress the ionization of the analyte. Okay, so in theory classes, you have read about the suppression of the ionization of the analyte. So the most appropriate answer for this question will be the second one, right? Okay. So the next question is related to the background correction. Why background correction is important? Very important in AAS because the signal of the analyte could be several folds higher, it could be several folds lower than the background signal, it could be adversely affecting the instrument stability or could be equal to the background, right? So if you are having a so much of background and analyte is signal is this one, okay, so background corrections is always lower than the background signal, analyte signal, right? So the second one should be the right answer for this. So there is a question on the limitation of background correction with continuum sources like deuterium lamp. Okay, if you are using the hollow cathode lamp, okay, that is a single wavelength source or primary source, you can say, and this one is continuum sources. So you have to define the capability of correction for this with continuum sources. Basically, the question is asking about with the help of this deuterium lamp, how much absorbance you can correct, or what is the limit of correction. Okay, so here are four options: more than zero point 0.5, more than 1, more than 1.5, and more than 2. Okay, if you have carefully read about this one correction due to deuterium lamp, you definitely know that. Okay, so I will wait for 2 minutes. I After that I'll explain. Okay, so the background corrections on flame AAS, basically using the deuterium lamp. So most of the spectral interferences and all other types of interferences results in attenuation of AAS signal to some extent. In general, the attenuation varies from negligible to several percent depending upon the metrics. Okay, so what it is um, describing. So if you are having this much of signal, right? If there is lot of background or lot of interferences, sorry, so they can suppress this signal, right? And it depends upon uh, the matrix of the sample. Okay, so this signal is known more commonly as background absorption, which can be easily estimated by aspiring a closely matching reference solution which does not contain the analyte, right? Basically, what you have to do, you have to record the reading for the blank. Okay, and after that you can subtract the absorbance of blank from the total absorbance, that is sample analyte plus blank, right? If you are subtracting analyte plus blank minus blank, you will getting the pure absorbance of analyte, right? Alternatively, what you can do, a radiation from a deuterium lamp can be measured at resonance wavelength to determine the background absorption. Okay, but here is a limitation. Background correction with continuum sources are incapable of correcting more than zero point 0.5 absorbance. So this is typically the question was asking about, right? So here is the mechanism of this background correction. Here you can see there is a hollow cathode lamp, and here is the deuterium lamp, right? If this is a monochromator and a spectral band pass of 1 nanometer, you will getting a single wavelength. But here, because this is a continuum source, you will getting a broad spectrum containing a large range of wavelengths. Okay, so you can see here if there is this much of signal due to uh, uh, this is a background correction. So basically you can reduce the background correction easily, like see here you can say the atomic plus background absorption is here, right? So you can easily subtract the, you can see this triangle, it is simply subtracted. Okay, right? So here in this way you can correct the background, or you can get the pure absorbance of the analyte, right? So the background correction, there is a limitation. You can correct the absorbance only up to zero point 0.5. So this one is the right answer for this. So the next question, uh, in the direct Zeeman effect, the magnetic field is applied to uh, you can say here is the source, and this is flame, and finally the detector. Okay, so in the Zeeman effect, what you have to do, you have to just basically apply the magnetic field, right? So there are two Zeeman effect you can observe. One is direct Zeeman effect, in which you apply the magnetic field to the directly to the source, right? And in the inverse Zeeman effect, you can apply to the flame, or where the atomization is taking place, right? So this is the basically first I will discuss about the um, Zeeman effect. So if there is no magnetic field applied, you will see only a one peak, right? If I applied the magnetic field, this peak will just split into three peaks. One is sigma plus, the other one is sigma minus, and one is pi. Okay. If atomic absorption spectrum is polarized parallel to the magnetic field, that is called the pi component. Or if atomic absorption spectrum is polarized perpendicular to the magnetic field, that is called the sigma component, right? So when the magnetic field is applied to the radiation source, it is known as direct Zeeman effect. The magnetic field can also be applied to the atomic cloud. This is known as inverse Zeeman effect. Zeeman effect. Okay. So how you can filter? If I'm get let's say if I want to get only the pi component, right? And how I can get the sigma component only, right? So you can see here, if if my polarizer is parallel to the magnetic field, what I will get? I will get only the pi component. Okay, and if my polarizer is is perpendicular to the direction of magnetic field, you will get the two sigma components. Okay, so here you can see the this is the signal magnitude. Okay, due to pi, and it is due to sigma. There is very little absorption. Okay, so simply you can subtract the background and you can get the true absorption. Okay, so here is the schematic for this. There is a source hollow cathode lamp, and this you can see here there are magnets applied to the atomizer or atomic cloud. That is called the inverse Zeeman effect. And if you apply directly to the source, that will be called the uh, direct Zeeman effect. So here you can write to the source and atomic cloud. Clear? Okay. So the next one in AAS, inverse Zeeman effect is preferred, but this requires, I have already explained, it requires a rotary polarizer. Okay, but what is the value of current and magnetic field in these parameters? So there are four options. That is a first one is a rotary polarizer. If a constant magnetic field is used. A rotary polarizer if an alternating current is used. A rotary polarizer if no magnet is used, or the polarizer is not required. Okay, so I'll wait for 1 minute. Okay, so this I have already explained, right? So atomic absorption instrument with inverse Zeeman effect are preferable. Okay, but a rotating polarizer is required if a constant magnet is used. So from this statement, you can tick this option. But what is the phenomena? Okay, in this configuration. Okay, let me see. Okay, in this configuration, absorbance is measured with the field off. That is normal AAS, and with the field on, you will get only the background. Okay, so this is a true double beam technique. Since both beams originate from the same source, measurements are made at the same frequency. They follow the same optical path and follow the same detector. The sensitivity remains unaltered, right? Okay, what you are doing basically, you are playing with the magnetic field. Okay. Yeah. You can see inverse Zeeman effect, the energy levels of the absorbing atom are split, and absorbance value also changes in the sigma components are rotated out of the radiation line, and only pi component absorbs, which can be measured. I have already explained this phenomena. So this is the various configurations of Zeeman effect in atomic absorption spectrometry, right? On the basis of location of the magnet, orientation of the magnet, and type of magnetic field you are applying. Okay, and what type of polarizer you have to use, right? Okay, if you are applying the magnetic field direct to the radiation source, there are two orientation. One is parallel, that is called the longitudinal Zeeman effect. Other is perpendicular, that is called the transverse Zeeman effect. And in the magnetic field, there are also two options. You can keep the magnetic field constant, and you can alternate the magnetic field, right? But in case of constant magnetic field, you require a rotating polarizer. And if you are alternating the magnetic field, there is no requirement of polarizer. Similarly here, right? So the correct option will be rotating polarizer is a constant if a constant magnetic field is used. Okay, right. Next is related to Smith-Hifze method of background corrections. What you do in Smith-Hifze, you basically apply the high currents to the source, that is hollow cathode lamps, And what is the reason? That is, first is there is no absorption at high currents, there is no absorption at normal current, there is no background at high current, there is no background at normal currents, right? So here is the explanation. So first, let me explain what is Smith-Hipge background corrections. So this method is based on the self-absorption behavior of radiation emitted from hollow cathode lamp when they are operated at high currents. Okay, the simple phenomena you can observe in the street light of sodium at high currents. They are release vaporized. They release the free atoms that can reabsorb the same radiation that they emit. Right. So this is the self-absorption behavior. Okay. So application of high current produces large concentration of unexcited atoms in the hollow cathode lamps. That is basically the background. And these atoms are capable of absorbing the radiation produced by the excited atomic species. So high current also broaden the emission line of the excited species. Net effect is to produce a line that is a minimum at its center. Okay, so you can see here this curve is at high current and this curve is at low current. So at high current, there is no signal due to analyte, right? So high intensity of electricity added to the source gives us more atoms, and when we have more atoms, then the chances for self absorption is higher. Okay, so one atom will get excited and then turning back will emit radiation. The other atom from the same radiation will absorb that emission, right? So in the beginning, the instrument measures the intensity of radiation at normal intensity of electricity, and after that, it makes the measurement on higher electricity. Okay, so the difference between them should give us the background absorption, right? Why? Because while we use a high current, the emission band became significantly broader, right? And when using a normal current, at the analytical wavelength, the emission intensity from the lamp decreases due to self absorption. This one is decreased due to self absorption, a process in which ground state atoms in the hollow cathode lamp absorbs photon emitted by the excited state atoms in the hollow cathode lamp. Okay, so basically, what we I want to say, when using a low current, I measure absorption from both the analyte and the background. Okay, and when using a high current, absorption is due almost exclusively to the background. So I can basically subtract the background from background plus analyte signal, and I can easily get the background, or you can say the analyte signal. So this approach is called the Smith-Hipge background correction. So there is no absorption at high current. So first option will be the right answer for this, right? So next one is related to the salt interferences. So if you are having a higher concentration of chlorides and sulfates in your sample, okay, so how they affect the AAS signal for most of the element. So why they affect? First is there is a formation of undissociated chlorides and sulfates. Second is formation of dissociated chloride and sulfates. Third is formation of oxides in the flame environment. And last is the suppression of free atoms in the vapor phase. Okay. So there is basically signal suppression is observed due to the chloride and sulfate. Why? Let's say if there is a flame here, and if there are some undissociated atoms present, or you can say the undissociated chloride or sulfate species. So this space where the analyte have to be uh, atomized, right, or absorb the radiation coming from the source. The space is already occupied by these undissociated chloride and sulfate, right? Same is written here. Since they do not efficiently atomize and produce absorbance, they can physically suppress the atomization excitation of the target element. As a result, the AAS signal for the target element get weaker, leading to inaccurate quantification. Okay, so there is no limit of background interferences, right? So you can get the anomalies in the quantification, right? So you can say there is a formation of undissociated chlorides and sulfate. So this one is the uh, right answer. Okay, right. So last question is, in the determination of calcium in presence of phosphate addition. Okay, La, that is lanthanum and strontium is preferably used. Why? Because it forms uh, the phosphates of these lanthanum and strontium. Calcium phosphate is not dissociated. Calcium oxide is formed, which is refractory in nature. Refractory means highly resistance to heat, or you can say these three, that is lanthanum, strontium, and calcium, form an easily dissociable alloy, right? So here you can see how the addition of lanthanum and strontium affect the analysis of calcium in the presence of phosphate addition, right? So it has been observed that for elements like molybdenum, vanadium, titanium, and these all is there is enhancement in the absorbance value, while there is no enhancement in the cases of less refractory elements like these. Okay, and the main point here, similarly with phosphates, it forms Ca3PO4 whole twice calcium phosphate during evaporation of liquid droplets in the flame. Okay, and this compound is converted to calcium pyrophosphate, which is very stable in heat. Right? If you are having a calcium phosphate, this on heating, it is converted to during evaporation of liquid droplets, that is desolvation. This is getting converted to calcium phosphate, which is very stable. Okay. So what you have to do, you have to basically introduce such kind of metal that can basically replace this calcium and form the salt of that particular metal. Okay. So this reaction reduces the free calcium atom population in the flame because that is very stable. Okay. So this type of interference can be eliminated by addition of a releasing agent, right? And releasing agents are basically preferred lanthanum, okay, that is basically combines with the interfering ion and release the analyte ion, okay. In other scenarios, you can use EDTA, ethylene diamine tetraacetate. You can use it as a EDTA can easily complex form a complex with metal, okay. So this can also work as a releasing agent. Okay. So the addition of lanthanum or strontium releases the calcium atom from the calcium phosphate, preferentially forming the phosphate of lanthanum and strontium. And the addition of EDTA preferentially form the calcium EDTA complex and easily volatile compound, which can dissociate relatively easily than the calcium phosphate. Okay. So this slide is basically taken from the lectures. So this type of interference can also be eliminated by the method of standard addition. So what will be the right answer for this? It forms the lanthanum and strontium phosphates, right? If I want to summarize this, what I will write: if there is a calcium phosphate salt during, it is in water, if desolvation is happening there, there is formation of calcium pyrophosphate, right? that is very stable in heat, and if it is very stable, you will not be getting the free calcium atoms in the flame. Okay, so what you will do, you will simply apply a releasing agent in the flame that will react with this interfering ions. It will form lanthanum sulfate, right, and release the calcium, and the concentration of free atoms are more. So that is the advantage of using the releasing agent, and you can, in this way you can easily eliminate the interference caused by the phosphate. Okay, so this was all about this assignment 5. I hope you liked it, and now I am just closing my session. Thanks everyone for attending.